Alright, welcome back. For the next video, what we're going to talk about is nonlinear effects. And when I say nonlinear, I don't mean non-additive, I mean non-rectilinear. So what we can have is we can have curvilinear relationships that get modeled with additive functions. And for this video and for the next video, I'm going to use the same data set, and I'm going to manufacture some data that allows us to test for these curvilinear effects. So the first thing I'm doing is I'm going to create an X primary predictor and a moderator. And the reason why I'm going to use a moderator is for the next video we're going to talk about moderated regression for nonlinear effects. So then I create a dependent variable that's a function of my X as well as my moderator. And as you can see here, it's just a lot of multiplication with some addition, what have you. Then I create a data set, and if you take a look at the plot of each one of these, you'll see that this is what the relationship looks like. That as you can see here, this is X on this, the X-axis, and this is Y, and this is what it looks like. Okay, so there's a curvilinear relationship with a little bit of, you see here, there's probably going to be a little bit of heteroscedasticity, and that's something we can talk about later. Okay, so when I model this, I'm going to model it using a standard polynomial regression. And what that means is I'm going to model it with X, and I got to change this a little bit, there we go, with X and X squared and X cubed. And the reason for it is I created an X squared and an X cubed, and as main effects as well as interactions. So what happens when I test that? So this is what I get. I'm testing the linear component, that's just X, the quadratic component, that's X squared, and the cubic component, that's X to the third power. Now you can see I'm accounting for a lot of variance here, 88%. This again is manufactured data. I'm just trying to make it so that it is abundantly clear what these things look like. Got to change some of these things because this is what I had before. And I want to show you what the effect looks like when we test it in that sequential manner that I talked about for interactions. Now, why is it that polynomials are relevant to moderated effects? Well, what happens is that these moderated effects that we were talking about before are multiplicative terms. But the multiplicative terms were multiplied two separate variables. So they were two predictors that were distinct. Well, in polynomial regression or in these curvilinear models, we have the same variable multiplied by itself. So if you go back up here, these are just weights. So it's X times 1. I didn't have to do it by times 1. I could have just left it there. Then it's X squared. So that's X times X. So the moderated effect is really just a variable moderating itself, which is kind of a weird idea. But if you think about X times X or X squared and X times X times X or X cubed, that is really not a whole lot different than a moderated effect, other than the fact that collinearity is going to be a serious issue because you're dealing with just the same variable, and a variable is going to be related to itself, and if what we can do is we can assess this correlation later. But what I want to do now is I want to look at what this relationship looks like in a sequential manner. So if you take a look here, that I'm doing a nested model comparison where the first model is my rectilinear relationship, right? So the second model includes the quadratic form, right? So now we have X and X squared in our model for model 2. And you'll notice that the p-value is a comparison. It's a nested model comparison between model 2 and model 1, and it shows that there's a significant difference. and that p-value is 4.3 times 10 to the minus 7th. Now if I come up here, I start out here, and my x is a significant predictor, but my x squared is not. But that's what I would expect that to be a significant relationship here, or a non-significant relationship, since my x squared is non-significant in my previous model. Similarly, for my model 3, I'm including my cubic component, and I get 2.2 times 10 to the minus 16th, and I get 2 times 10 to the minus 16th here. So I'm getting similar values, but not the same. And remember, if I take the t and I square it, so 20.48, and if I take 20.48 and I square that, I get 219.43, which is approximately this f value right here. So my last value, this x cubed, is approximately the same, if not identical, to what I'm getting in my nested model comparison. And this is very similar to what we were observing in the previous videos, where we had a hierarchical testing of these effects, where these sandwiched effects, these effects in between the last effect, did not have the same parameter estimate, didn't have the same hypothesis test. And the reason for that is because of multicollinearity. Nevertheless, all of these effects that we're testing here are collinear. Now, what would happen, what I'm doing here is I've just manufactured data, or I took this data, but I put in new variables. I put in x2 and x3 to represent x squared and x cubed. So you'll see that in your second data set for this coming week. And what I wanted to show you was the correlation matrix among our different parameters. So or among our different predictors and variables. So you can see x and y have a minus 0.58 relationship. And our moderator has a 0.25 correlation. And then x and x squared correlate 0.12, and x and x cubed correlate 0.76. So this tells you that there is a fairly high collinearity, or there's multicollinearity in our model. And if I do VIF for my LM5P, you'll see that there's fairly high VIF values. And those high VIF values might have influenced the tests of the hypothesis tests. But if you go back to the entire model, you'll notice that x and x cubed are both significant. So VIF affected it, but not sufficiently enough to change our decision. And the VIF for x squared was relatively low, close to 1. It's 1.1, and yet it was non-significant. Okay, so there could be a situation in which the collinearity affected our parameter estimation and our hypothesis testing for x squared. So what does all this mean? It means that these polynomials are collinear, and they do affect hypothesis testing. Now there is a way in which we can test these models with what are called orthogonal contrasts, and these are orthogonal polynomial contrasts. And what it does is there is a way in which we can create a set of contrasts where each of our predictors is orthogonal to one another. Now remember back to what you learned in data aggregation. If we created principal components, we could create 3 orthogonal principal components because we have 3 predictors, and those orthogonal principal components wouldn't necessarily be the terms that we cared about. The terms meaning we want a linear, quadratic, and cubic term in our model. So we could do that with PCA, but there's less control. So instead what we can do is set up orthogonal polynomial contrast, and we're going to talk a lot about this when we shift over to dealing with categorical or nominal level data as predictors. But these polynomial contrasts are independent. They create independent predictors, and so you can see our parameter estimates are now different and our hypothesis tests are different. The amount of variance that we account for in our model remains, remains relatively similar. 88.29, 87.93, and this should be 88.29, 87.93. So the amount of variance that we account for in our dependent variable remains the same. Parameter estimates, hypothesis tests change. Look at here. This middle term is our quadratic component. Now it's significant. And the reason why it's significant is it's no longer collinear. It's now a transformed variable such that our linear, quadratic, and cubic forms of x have a correlation of 0. Okay? And when we do that, we are now getting, and I can show you, if we test these in this hierarchical way, we should be able to produce the identical p-values for each step, and indeed we can. And that's what you see here. Each one of these steps, 4.27 times 10 to the minus 7th, 4.27 times 10 to the minus 7th. Remember, they're just truncated at that level. So we can get each step here. You can reproduce these f values, just square the t's, you'll get these f's. And that's what you're going to be doing a little bit of this week in our in-class assignment, is we're going to work through some different data sets. We're going to manufacture data this week because I want everybody to be familiar with how to create data. And once you create the data, you'll have a much better understanding of what to look for and what these parameter estimates should be. So you already have the basis for how to create data. You also have the basis for testing interactions from before, but now we're testing interactions where the interactions are for the same variable. And that's the thread that ties together all of this, is that before we were talking about dissimilar variables, now we're talking about the same variables, so that we can model these non-linear, meaning non-rectilinear relationships between x and y. In our next video, I'm going to include m in our model so that you can see what happens when we have a moderated effect with these non-linear components, non-rectilinear components. So stay tuned for the next video, which will be the concluding video for the novel material, and then I'll finalize it with the in-class assignment. So stay tuned for that.